All right. Well, how's everybody doing? Good. All right. Thanks for that enthusiastic response. Oh shoot, what did I do? I just closed the program, I think. All right. We're sorry. OneNote is cleaning up. Okay. No? All right. That's fine. No need to apologize. OneNote. Okay. So today's topic is going to be neural networks. All right, and it's just going to be a very. Let me write so you guys can see. Like a very, very, very basic introduction to the subject of neural networks. A lot of, I guess, research and work is being done in this field right now, and you can take an entire course on neural networks. If I were allowed to teach another course, I think I would enjoy teaching a class on this subject. But we'll just spend 1 week on it, and it'll just give you this very shallow introduction to this stuff, and yeah, you can learn more. Anyway, so the idea about neural networks is, you can use them for regression in terms of predicting a numeric output, or you can even use them for classification in terms of predicting a categorical output. The idea is things are set up in what, I don't know, I guess scientists believe the brain is set up in terms of like having, these brain cells, neurons that are connected to each other. And I guess at some very basic level, our brains are just these interconnected neurons, and they're just firing electric impulses, and they receive impulses and fire more impulses, and somehow that collection of impulses firing on each other gives our ability to think and reason and have consciousness and stuff. We don't have a whole lot of understanding of exactly what, what set of neurons. I mean, there's a lot of brain research and stuff, but, the way our brains work is still a bit of a mystery. And similarly, when we go to neural networks, you don't have a whole lot of reasonable interpretation coming out of the neural network. Okay, you can set it up and train it so it can make good predictions. But if you come back and you say, what does this coefficient mean? Is there any significance to it? That's not really available. Unlike linear regression, the coefficient has a very interpretable thing. Even logistic regression, it's not as interpretable because you're dealing with odds ratios and stuff, but there's still some kind of interpretation here. I think with neural networks, when you look at the coefficients, it's really, really hard to interpret at all. I'm basing my lectures off a series of YouTube videos. There's a lot of stuff out there on neural networks. I found this series. I've linked to it on the class website. I found the series to be very very good, and so I'll kind of follow along here and explain. And so we're gonna just start off with this tiny data set, okay, where we've got inputs X and we have our output Y. Okay, and this is going to be a regression neural network, and in that we have some numeric inputs, and our outputs are also numeric. So we've got 3, 5, 1, and 2. So the example in the video is hours of sleep and hours of study. And how does that affect, a score on a test? And looking at this, there seems to be a strong relationship between how much sleep the person got in the score, or I don't know, who knows, okay? But anyway, so the question is, so this will be our training data. And this is, very, very, very small. And so it's going to be hard to do this. But basically, we use this data to select the coefficients of our model. Okay, and then the test case is, you'll have some inputs here. And the question is, what is your predicted output? And so what we'll use as our model will be a forward feed neural network. Okay. Okay. And so in our data, we have two input values, okay? We have two input values, 3 and 5, and an output value, 75, or 5 and 1, and the output value, 82. Okay, so we have two input values. And so in our input layer, we will have two nodes. So we'll create one for x1, and we'll create a node for x2. And we can say this will be hours of sleep and hours of study. Okay, and in a forward feed neural network, you'll often have something called a hidden layer. And so just arbitrarily, I will choose to have 3 nodes in the hidden layer. Okay. But if you wanted 1 node in the hidden layer or 10 nodes in the hidden layer, that's up to you. Okay. And then because we only have 1 value to predict, our output layer just has 1 node. And this will be, kind of our output score y. And the way the neural network works is that each node connects to all of the nodes in the next layer. Okay, so this node will connect to all 3 nodes in the next layer. And this node will also connect to all 3 nodes in the next layer. All right, and so this is the forward feed part, okay? These 3 nodes will all connect to all the nodes in the next layer, of which there's only 1. So each of these will just look like this. So this is what our simple forward feed neural network looks like. More advanced neural networks can have like multiple hidden layers, okay? And just you might have something like this, where you've got a bunch of one output layer, and you have all of these connections, and each one is connected to every single one. All right, and there's just so many lines to draw. Okay. and there's going to be you know, lots of connections to draw, and I don't know, whatever. All right, and all of this, having all of these extra hidden layers, many hidden layers, people might call this deep learning. So if you've got a bunch of hidden layers in your neural network, you know, we can call that deep learning. But it's just still the idea of this kind of this forward feed where, you know, you've got a nodes in the input layer, you've got some hidden layers. Every node is connected to every node in the next layer, and they feed forward in that regard. Okay. All right. So what does it mean for the nodes to be connected? The idea here is let's just take a look at going from our input. So we have x1 and x2 going to our hidden layer. All right. And so what do these arrows even mean? Okay. Well, the idea here is that we're going to take our x values. Okay, so here's my input matrix x. And I think the values I have are 3, 5, 5, 1, 10, and 2. Okay. And if we just take a look at this this thing, I'm gonna call this Z. Okay. We'll call this will be Z1 and this will be Z2. This will be Z3. What we're gonna do is we're gonna say, okay, the values that come into Z1 will be basically going into Z1 and sorry, to kind of indicate that this is, the notation here to indicate that this is in the second layer. Okay, so Z1 in the second layer, this is going to be equal to our x1 value multiplied by some weight. Okay. And x2 multiplied by some weight here. Okay. We're basically going to multiply our input matrix x, which is currently a 3 by 2 matrix. All right. It's 3 by 2 because we have 3 training cases, training examples, and we have 2 input x variables. Okay, if you had 100 training cases, it would be 100 by 2. And we're going to take x and multiply it by a matrix W, so that when we do this, we're going to get each of these relationships. So Z2 will be the result of x1 times W12 and x2 times W22. And Z3, this is so what I'm just showing that the relationship is going to be an X matrix here, which is 3 by 2. We're going to multiply it by a W matrix. Okay, in the first layer, this is going to be 2 by 3. And this will produce our values in the Z matrix, which will be 3 by 3. Okay. So I have 3, 5, 5, 1, 10, and 2. And then here I've got a 2 by 3, which will consist of 1, 1, W12, and W13, W21, W22, and W23. And this will produce, for each row, the values Z1, Z2, and Z3, but for one for each training case. Okay, so we have so this is 2 by 3 because we've got we have 2 inputs, 2 input nodes, and 3 nodes in the hidden layer. Okay, and this we have 3 rows. This Z matrix is 3 by 3. Okay, 3 rows for we have because we have 3 training examples. And 3 columns because we have 3 nodes in the hidden layer. Okay, so we have, so each of these lines here represent one of these W weights. Okay, so X1 going to here, this is going to be weight 1, 1. This is going to get hard to draw. This is weight 1, 2, and this is weight 1, 3. And then this arrow here is going to be weight 2, 1, weight 2, 2, and weight 2, 3. Okay, I don't know if that makes sense. So each arrow corresponds to one of the coefficients in my W weight matrix. Okay, and the idea here is that you have these input values x1 and x2, and we're just going to weight x1 and x2 by some mystery values, w1 and w2, and when they combine together, they combine and they form z1, z2, and z3. Okay, and this will happen for each value in your input matrix, or each row in your input matrix. So again, if I had 100 training examples, it would be 100 by 2. Okay, this weight matrix is still the same, going to be 2 by 3. So you would have 100 by 2 times 2 by 3, and your output would be 100 by 3. Okay, you would now have 100 rows because you have 100 training examples, and each one of those rows has values in the hidden layer Z. And so you've got this 3 by 3, or now a 100 by 3 matrix. Okay, is that all right? Okay, and so we have that, and that is going to be our the values there. And then what we do is, if we look at this, those values Z will then kind of combine together. But actually, before we start just multiplying z's, we apply a function to these z values. Okay, so we apply an activation function to each value in the Z matrix. Okay. So you just have some kind of function here. So you have matrix Z, and then you apply a function. Okay, so you take some function on matrix Z, and you'll get another matrix A. All right, so in our case, Z has, I guess, dimensions n by 3, and A will have dimensions n by 3. In this case, I guess we have n is equal to 3 training examples. And so, you know, A will also be 3 by 3. Okay, you're just going to apply some function to each element in Z, element-wise, and so you'll have another matrix of the same shape as Z. It's just the numbers that were in Z have been transformed to another set of numbers. Okay, so we apply a function to each value in the Z matrix. Okay, we get matrix A, which has the same dimensions as Z. Now all we've done is just apply some function that just maps one number to another number, right? So that's all a function does. It just says, oh, your input number is this, the output number is this. Okay. And the function simply maps input number Z to an output number A. Okay, that's all. Okay, and then so we'll call this to just kind of indicate that this is happening in the second layer of our matrix. We'll put a little superscript 2. Okay, and so after that, so I guess my picture here looks like okay. So going in, you're going to get, kind of Z1, Z2, and Z3, and then you apply some kind of function to it. And you're going to just get a different number out here, A1, A2, and A3. Okay. And then we take these values A, and we combine them right here with another matrix W. Okay, so we will have kind of W11, W21, and W31, and this is our second weight matrix. So we're going to put a superscript 2 here. Okay, so we take, after applying the function, function f to each z value, okay, we have A values, okay? And then we multiply A by another matrix W. to weight the values. So, so A, in our case, is going to be n by 3, or 3 by 3. And then we multiply it by W. Our second, another matrix, W2. And so what will the dimensions of W2 be? It'll be 3 by 1. We have 3 nodes coming in and 1 node going out. Okay, and so this will be W11. I'm sorry, wait. 3 by 1, that needs to be a column. So 3 by 1 is a column matrix, W11, W21, and W31. And this will form, you know, our set Z in kind of our third layer, all right? And this will just be one value, but it'll be kind of n by 3. So I'm gonna, instead of writing 3 by 3, I'm gonna just write n by 3 to kind of emphasize. I'm sorry, n by 1. Yeah, n by 1. Okay, so you'll have just kind of a z value for each thing. Okay, so Z3 will be the combination of basically A1 times W11 in the second layer plus A2 times W21 in the second layer and A3 times W31 in the second layer. Okay, so we're, yes?
Can you move the screen to the right a little bit?
Can I move the screen? Oh, like that?
Yeah.
Okay, sorry. Yeah. Nothing else is coming up, getting cut off the screen. Just says we multiply A by another matrix. Okay, and so now we have a single Z value for each input row, and then we apply just another function, another activation function, and then finally, we apply another activation function to Z. Okay, and so we just apply function to Z, and we get, and this will form our prediction. This is our predicted value. Okay, and Z is n by 1, and y hat will also be n by 1. So however many inputs you have, you're going to have that many predictions, which makes sense. Okay, so that's the forward feed. Let me kind of just summarize forward feed summary. So our picture, we've got x1 and x2. we've got 3 nodes here. So we apply the input x's, get applied, basically some weight values. Weight, okay? All of these weight values get applied and they form these z values, okay? Then the z values get a function applied to them. And these form a values. A1, A2, A3 in the kind of the second layer. And then those get weighted into a single z value. And then we apply a function there, and that's going to produce our y hat value. Right. So our x's come in, we just multiply them by some weights, and we get some z values. For each of those z values, we apply a function f, and we get new values a. Those values a, we multiply by another set of weights, w, okay, our second weight matrix. And we get another set of z values, and then we apply a function, and there it's just one z value, we apply a function there, and that's going to be our predicted value y hat. Okay, so in matrix notation, we're going to have x, and I'll go ahead and I'm going to just underneath put the dimensions of each of these things. Okay, we have n by 2. Our first weight matrix, and this is going to produce our z matrix and the that, okay? Then we apply f to z, and we get back a, and then we apply multiply a by w, our second weight matrix. So a is n by 3 and w is 3 by 1, and this will produce z. And the third layer, and this is going to be n by 1, and then we apply a function to z, and we get our y hats. Okay, so this is the matrix representation of this picture. I hope that makes sense. Yes, question.
Whether the two functions are the same function.
In our case, we will use the same function. It is not a requirement that they be the same function. And I would say in most cases, we end up using the same function. We just kind of keep our lives a little bit easier in that regard. But it's not required that they be the same function.
Are you talking about the same function across nodes or across layers?
So yeah, between the two layers. Okay. So the first, so you would use, for the first node, or first layer, you would use the same function across every single node, okay? And then the second time you use a function, in this case there's only one node, that function could be different from the function you used over here. In general, we use the same function, okay? In general, we use the same function, but it's not required to. But yeah, for one layer, you got to use the same function for all the nodes. Yeah. Okay. Sometimes you might include something called a bias. Okay. Some layers may, I didn't draw them here, but sometimes layers might have a bias applied. Okay. And the way that looks like, okay, and that basically says, we're just going to, before we apply a function here, so we have x times w and we get z. Before we apply a function to this z, we just add basically, yeah, I'll draw this. It's just, instead of trying to like squeeze them, squeeze it in here. How do I do this? How do I? Okay. Sorry, just trying to figure out how to organize this. So sometimes a bias is applied to the layers, and basically, here I've got z2, which is n by 3, and here we would add basically a B matrix, which is basically before we get our values A. Okay, and so B is, I guess, a 1 by 3 matrix of constants. Okay, but then it would get kind of duplicated across all n rows. Okay, and then it gets duplicated across the n rows. So this is technically 1 by 3, but times n. So B is a 1 by 3, but then you duplicate it n times, so your dimensions match up. Okay. And basically, and you can do that any time before you apply the function to the thing, and that just, it's like adding an intercept. It just gives you an extra coefficient to estimate and extra, I guess, freedom in terms of, or flexibility in terms of the network that you're trying to fit. Okay, so just adding, using a bias, using bias values, just provide more flexibility to the model. All right, is this okay? So the idea, just, so, neural networks, I don't know if you guys are familiar with neural networks prior to this, but I don't know, there's some kind of, sometimes there feels to be this like mystery or aura around them. It's not anything special. You're just taking some numbers, multiplying by stuff, applying a function, multiplying those things, applying a function, and you're just doing this sequence, and after you do all of this stuff, you get some number output. Okay, and so the question, but somehow we've been able to get really good predictive results out of neural networks, right? I think probably the biggest application of neural networks is for like image recognition these days. You give it this picture and you feed it into this deep learning neural network, and it'll say, there's a dog in this picture or something, and it's like, wow, how did it do that? And it's a mystery, but at its core, it's just multiplying by weights, applying functions, multiplying by weights, and applying functions, and that's all it's doing. And it's somehow that process is able to give good predictions, and it feels quite mysterious. And it just comes down to what are these weight values we use? We just have to estimate these weight values, and if we get good estimates of the weight values, we're able to make good predictions. Yeah, question.
So yeah, I was wondering what do we get in weight?
Yeah, where do we get the weights? Yeah, that's a very, very good question, and that comes in when we'll get to training the neural network. Okay, and that training the network just means, can we figure out these weights to use in the weight matrix? Okay, I know, like, training a model sounds a lot fancier. Like, it's just, let's figure out some good weights to use, and we'll talk about what it means to get good weights. Okay. Yes. Question.
Can you talk about, is there any intuition or theory behind the choice of the number of layers or the number of nodes within the layer? I don't know, some application in R that could maybe
Yeah,
guide you
no,
with those choices?
it's like totally arbitrary. Okay. I hate to give you that answer, but there's
That's what it is.
yeah, it really is arbitrary in terms of, because I guess at the heart we don't know what these weights mean. Like, we have a way to pick good weights and train the model, but we still don't know exactly what the weights mean, and the mystery between having this many nodes versus that many nodes, it's just, do you need additional flexibility? Like, is your model too rigid? Then add more nodes in the hidden layer. So in this case, I've got kind of, our input variables are x, and we've got one output y. So we probably don't need to go overkill and put in 100 nodes in the input layer, but I mean the hidden layer. But we could. But yeah.
So you're saying it's sort of like in that statistical learning textbook, they set up this paradigm about bias and variance trade-off.
Mm-hmm.
So if you're sort of underfitting, then maybe you would add
Right.
nodes.
Yeah.
And if you're overfitting, maybe you would take them away or something.
Yes. That's kind of our guiding principles, right? Is we can add more parameters to estimate, and that will mean our model will have more flexibility. We might end up overfitting the data that we have. Okay. On the other hand, we can take away a bunch of these parameters to estimate and say there's only a few, and we might underfit our data, and it's that bias variance. So if you have too many things in the hidden layer, your variance will be high, and if you have too few, your bias will be high. But can we definitively say, oh, you should use 100 in this case versus 120 or 150? No, we don't fully understand the differences between them right now. So it is a little arbitrary. Okay, let me just talk about this activation function. Okay, and there's all sorts of choices. Today, I'm going to kind of use this classical activation function, which recently has maybe fallen out of favor because of the derivatives are not as easy. But okay, so the activation function f. Okay, and so a common choice is the sigmoid, basically logistic function, which we saw it for logistic regression. For whatever reason, when we use it in neural networks, we often call it the sigmoid function, and that takes inputs from negative infinity to plus infinity, and remaps them on the range 0 to 1. Okay. So if you have some value t, this becomes 1 over 1 plus e to the negative t, or I guess it's the same as, okay. And so this, and we will often scale our input values x to be in the range from 0 to 1. Okay, there's other choices, okay? Other choices for activation functions. Another popular one is the rectilinear. Which just looks like this. At 0. But anyway, we'll go ahead and we'll just use the sigmoid function for our simple neural network here. Okay. Okay. So training the network. Okay. This just means figuring out what some, quote, good weights are for the W matrices. Okay, and so if we think about it, all right, so we've got, so here's our, okay, so our W1 matrix is 2 by 3. And then our W2 matrix, so these are W1s over here, and then our W2 is a 3 by 1 matrix. So we have a total of 9 weights to figure out. Okay, and so when we say let's train our matrix, we're going to use an objective function. And in this case, our objective function will be, let's measure how different is my prediction from the actual value. Okay, and we want to minimize the difference between our prediction and our actual value. Okay, so we have 9 weights to figure out, and we will I guess measure how good these weights are by using an objective function. Okay. An objective function, sometimes this is called a loss function. All right, so objective meaning like what's your goal, or the loss will be, in this case, because our goal is to minimize how different our predictions are from the actual things, we can also just say the loss is how different they are, okay? So, so our function will measure how different the prediction is from the actual value. So we'll say, I'm going to call this L, and this will be the sum of our actual value y minus our predicted values squared. Okay, so this will just be sum of squared errors. So this is the actual, and this is our predicted. Okay, keep in mind our predicted value y hat is the result of basically our x multiplied by our w1, where we've applied a function, and then we take that result and we multiplied it by a w2, and we applied a function there, right? So we took our x's, we multiplied it by weight matrix 1, applied a function there, multiplied it by weight matrix 2, and applied a function there, okay? I know, it's just this, okay? So x times w, applied a function, multiplied that by w, applied another function, okay? But, so this is how we're getting our predictions, right? So this is our, okay? And if we had biases, then we would add our bias things in there. Okay, and so we want to, so you would have some values w, and then you'd say, how good are these? And then you can say, well, let's try out some new values of w. And basically, we just want to find the matrix, the values, these 9 values in weight matrix 1 and weight matrix 2 that will minimize the sum of squared errors here. Okay, so this is our goal. We want to find the set of w values that will minimize the sum of squared errors. Okay. So how should we do this? Okay. Well, this is just a function, okay? It's just you have your data, and then you can replace y hat with this, and you've got some kind of function that we just want to minimize, okay? This function L, how many inputs do we have? This is the value of L. So if we treat our data as fixed, how many values do we have? How many variables go into affecting L, our loss? Huh? N? It's 9, okay? So our loss depends entirely on these 9 W values that we don't know, okay? Because we're going to treat our data as a fixed set. Our data is not variables, okay? There are data, and we just want to minimize our function L as a function over these 9 mystery weights, okay? So we want that will minimize the sum of squared errors. So our function L is a function of these 9 mystery weights. Okay, so it's a function of 9 variables. At least in this case, right? For this neural network. Okay. We treat the data y and x as fixed values. Okay? They don't vary. They are fixed, and so when we are training, we are just trying to minimize our loss as a function of these nine values. Okay. I don't know if you're familiar with how to minimize multidimensional functions or optimize them. Okay, so it's tricky. Okay, so we have a multidimensional function, a function of 9 variables, and we want to try to minimize it, and it's not easy. So we compromise, or not compromise. Our best solution is to use something called gradient descent. Okay, and this is not it's not guaranteed to find a global minimum. Okay, but it's pretty decent. Okay, it's easy to implement, and so that's why we like to use it. But it's not. It certainly has its shortcomings. Okay, so a practical solution for minimizing this function of 9 variables is gradient descent. Okay. All right, so gradient descent. So you can think of gradient. The gradient is basically the derivative, but for a multidimensional function. Okay, so the derivative is the slope of a function. When you're talking about a univariate function, the derivative is basically the slope of the curve at that location. Right? The gradient is similar to that, except it's in a multidimensional context. So, my brain has a hard time imagining more than 3 dimensions because that's all I've experienced in my life. So, so I can only really think of like a 2-dimensional thing and a function applied over 2 dimensions. And so basically, so here, let me just kind of, so the gradient is basically a multi-dimensional derivative. All right, and so for a univariate function, the derivative is the slope of the function at a location. Okay, and basically, let's say the gradient of a multidimensional function is basically the slope also, and it's also the quote slope, but it's basically a multivariate vector pointing in the direction of what is uphill. Okay, so there's also the slope, but this time it is a multi-dimensional vector pointing in the direction of what is, quote, uphill. So if you've got, I don't know, some surface that looks like something like this, right? And this is like a terrible drawing here, but if you're located here, okay, the gradient might be some kind of vector that points, and we'll say this is the way to climb to the mountaintop. All right. I don't know how to draw. This is bad. Okay, but so it's just saying, this, it's not straight up. It's along the hill. Okay, that's what that's supposed to be. All right, and it's pointing to it, and it's just which way is uphill. All right, and the way gradient descent works is basically you're at some location, you take the gradient or the derivative at that point, and it says, okay, this way is uphill, and you say, okay, if that's uphill, I'm going to go in the opposite direction and go downhill, okay, because I want to find the minimum value, so I'm going to go downhill, okay, and you just, in gradient descent, you just take a step downhill, and then you recalculate which way is uphill, and then you say, okay, if that way is uphill, now at my new location, I'm going to take another step downhill. And so basically, you're just taking tiny little steps, and you go downhill, right? And you can think of it as, you've got some kind of rolling hills landscape, and you just set a bowling ball somewhere, and the bowling ball is just going to roll downhill, okay? And except this bowling ball has no momentum, so as soon as it hits the bottom, it's going to stop. It's not going to try to keep climbing, and so you just let this ball roll down, and then and it reaches some valley, and then it stops, okay, and you can see just visually that you're not guaranteed to reach a global minimum, because if there's a local minimum, it's just going to stop there, but it should get us downhill, okay? Wherever we start, the ball should roll downhill, and then when it reaches the bottom of wherever it got, it's going to stop there, and that's going to be better than where we started. And that's that. There's no guarantee it's going to find a global minimum, so a strategy is let's start rolling bowling balls from different locations and see where they go, and if a bunch of them kind of converge to the same low point, we'll say, all right, that seems good enough for me, but it's not very rigorous in the mathematical sense. Yeah.
Does that mean that it's vulnerable to, if you had a bunch of predictors and a handful of them were totally not correlated with the outcome, does it make the neural network setup vulnerable to that? Because, to use your rolling hills analogy, maybe there's a whole bunch of valleys that are just sort of random.
Yeah, I mean, if you have a whole bunch of inputs that are unrelated to the output, we're hoping that in the training of the network, eventually the network will just say, these things aren't super important. There's not the way we train the network, there's not a penalty for having a bunch of coefficients that just are small versus zero. There's not a penalty of zero versus small coefficients, and so you probably won't have, they're probably not going to remove all of these things that are useless in terms of making predictions. But, and so you might have several locations that, I don't know, in this analogy, that we might be stretching a little too far, there might be this large flat valley, okay, where, whether you mess around with these predictors, it doesn't really affect the thing. And so, you might start bowling balls from different locations, and they just reach the bottom of this flat valley. And so the weight matrices at the end of the day are totally different, but as far as the predictions they're making, they're ending up being the same, okay? And that's kind of all we care about. In the neural network, we don't actually care so much about the weight matrices, again, because we don't even know what they mean. But if it's making good predictions, we go, hey, that's great, okay? And that's that, okay? So so anyway, what was I saying? Okay, gradient descent. So yeah, the gradient is the multidimensional derivative. And so gradient descent just says, you know, start at some location, find the gradient, okay, and take a small step in the opposite direction. So that will be downhill. And then keep taking small steps downhill. Okay, until you are not moving. And so I don't know, like here's a kind of a univariate example. So let's say you have some function that looks like this, okay? Now visually we can see this is going to be the bottom, right? But we're going to start here. This will be x1, or I don't know. We'll just start here, okay? And we say, okay, what is the slope? The slope is going to be, you know, the rise over the run at this thing. And we say, okay, well, here's the, I need a better color. So the slope at this point goes like this, and we're going to just take a small step downhill. So we go, okay, I'm going to take a step here. And then we say, okay, I'm right here, and I'm going to just take a small step downhill. And here I'm going to take another small step downhill. And this is all we do, okay? And then as we get here, our slope gets more and more shallow, so the size of our steps get even smaller and smaller and smaller. But we're just taking small steps. Oh, no, that doesn't seem to actually be as illuminating as I'd hoped. But it just looks like I'm drawing arrows down the hill. But that's all we're really doing, okay? So, you know, if we're currently at x at time location n, we basically just subtract off the derivative of the function at x at time n, and this will be x at time n plus 1, okay? The next value is just take this, so because the derivative here is positive, right? Because the slope is rising at this point, and so we move in the opposite direction of what the slope says, okay? And as we get closer to here, our slope gets closer and closer to 0, so the steps we take get smaller and smaller and smaller. And so at some point, we're just taking, we'll never, based on this method, we'll never actually reach the minimum. We're just asymptotically approaching it, okay? Because we're just taking further, like smaller and smaller and smaller steps, right? But, and so that's all we're doing. Okay, so how do we take derivatives with respect to this this loss function? Okay, so all right, so we're going to have to do some matrix calculus, which, you know, maybe you've done or you haven't done. You can think of gradient. Okay, so we're gonna find the gradient of our loss function W, or loss function L. Find the okay, so this involves a little bit of matrix calculus. And some of the rules for matrix calculus might be a little confusing, but the big rule is kind of like when you take the derivative of a matrix, the derivative should have the same, or the gradient should have the same dimensions as that matrix. Okay, so when you take, or when you, when you take the derivative of a function with respect to a matrix, I keep getting my terms mixed up. When you take the gradient of a function with respect to a matrix, the gradient will be another matrix that has the same dimensions as the matrix. Okay, that's going to be kind of one of the guiding principles, right? So the gradient of a function with respect to a matrix will have the same dimensions as the matrix. So it'll feel like, oh, you're just throwing transposes and stuff in there. Well, we're trying to preserve these matrix dimensions. Okay, so when we say the gradient of a function L, it looks like this. This is basically gradient of L looks like this upside down triangle. And we're going to have two gradients to figure out, okay? We've got the gradient of L with respect to weight matrix 1, which is a 2 by 3 matrix. And so this will be, we can kind of write it this way. It's like the partial derivative of L with respect to weight matrix 1 will also be a 2 by 3 matrix. And then the gradient of L with respect to W2, which is a 3 by 1 matrix, will also be a 3 by 1 matrix. And then gradient descent, okay, and then, so just kind of fast forwarding where we are headed. Is, you know, once we find our gradients, we can use gradient descent, which will basically be the next, given our current values, so our current estimate of, you know, some matrix W at time n, we improve them by taking a small step opposite of the gradient. I should say Okay, so this is gradient of L at location Wn, and then just a small scaling factor. And when we do that, we will get our next value to use. Okay, we can use gradient descent. So we're going to take our current estimate of W, and basically this this part is basically taking a small step downhill. Okay, in the same way that subtracting off the derivative at the location will get you closer towards the minimum. We take a small step downhill like this, and we get the next value to use, and we just iterate. Okay, so this is where we're going. Okay, so there's a, let's see, 7:18. Okay, why don't we take a short break here, and then when we come back, we'll dive into the, I don't know, it's not so bad, the calculus involved in calculating these gradients out. Okay.